Singapore, February 15th, 1942, 8 a.m. Lieutenant Commander Haruto Ishikawa opened a captured British radar manual expecting serial numbers and wiring diagrams. Instead, 3 words froze him in place. Yagi Array Antenna. The name was Japanese. The invention was Japanese. The equipment was not. Hey everyone, if this story hits you, hit that subscribe button. It's free. It helps more than you know. And drop a comment telling me where you're watching from. Now settle in, because what you're about to hear changed the course of the Pacific War before a single bomb fell. The captured British radar facility on Bukit Timah Hill still hummed with electrical current. Fluorescent lights flickered overhead as Ishikawa's boots echoed against cold concrete floors. He'd been sent to catalog captured technology, a routine intelligence assignment, serial numbers, frequency specifications, perhaps a few technical manuals to ship back to Tokyo. He did not expect his hands to start trembling. Technical Specialist Lieutenant Arai met him at the main operations console, holding a thick British manual bound in canvas. The young engineer's face had gone pale, his usual composure replaced by something Ishikawa couldn't identify. Confusion, disbelief, fear. "Commander," Arai said quietly, "Page 47. You need to see this." Ishikawa opened the manual. Technical diagrams, component specifications, antenna configurations, standard material. Then his eyes locked onto 3 words printed in bold English: Yagi Array Antenna. He stared at the text. "Read it again." The letters seemed to swim before his eyes. Around him, 4 other Japanese engineers had gathered, their conversation growing heated. "It must be a code name," one insisted. "British designation for their system. Deliberate misdirection," another suggested. "Allied intelligence creating false documentation." Cross-reference the patent citations. For 20 agonizing minutes, they debated every possibility except the one that terrified them most. Ishikawa reread the technical specifications, cross-referenced the antenna diagrams, examined every patent citation listed in the appendix. Every reference pointed back to the same source. Every calculation confirmed what he desperately wanted to deny. Finally, Lieutenant Arai asked the question that would haunt Japan's military leadership for the rest of the war. "Sir, could Yagi possibly be Japanese?" The room fell silent. Ishikawa's chest tightened. He knew Professor Hidetsugu Yagi. Every educated officer in Japan knew of him. The brilliant researcher from Tohoku Imperial University who had invented a revolutionary directional antenna in 1926. An antenna that could focus radio waves with unprecedented precision. An antenna the entire world had apparently adopted. An antenna Japan's own military had somehow never deployed. He looked down at the British equipment surrounding him. The radar sets hummed steadily, their Yagi arrays mounted on rotating platforms, scanning the skies with mechanical efficiency. These were the systems that had given British forces advanced warning of Japanese air attacks. These were the antennas that had helped coordinate Allied defenses across Southeast Asia, all built using Japanese-invented technology against Japanese forces. In that moment, standing in a captured facility on foreign soil, Ishikawa realized they weren't just looking at enemy equipment. They were witnessing proof that Japan had fundamentally misunderstood the nature of modern warfare. The British hadn't just adopted Yagi's invention, they had perfected it, mass-produced it, integrated it into a comprehensive radar network spanning continents. While Japan's own military services had apparently ignored their own scientists' breakthrough, one of the engineers spoke, his voice barely above a whisper. "If the British are using Professor Yagi's design," he trailed off, unable to complete the thought. Ishikawa finished it for him. "Then we must assume the Americans have as well." The implications settled over the room like volcanic ash. For months, Japanese military briefings had assured officers that Japan's scientific capabilities matched or surpassed Western technology. Those briefings had been politically shaped, carefully curated to support strategic assumptions. Now, staring at concrete evidence of organizational failure, Ishikawa saw those assurances for what they were: comforting illusions built on incomplete information. If Japan had ignored Yagi's antenna, an invention created by their own scientists, published in their own academic journals, what else had they missed? What other breakthroughs had Japan's fractured military services failed to recognize while their enemies weaponized them? And if this was what the British had built, using Japanese technology, what had the Americans, with their vast industrial capacity and integrated research programs, already developed? Ishikawa closed the manual slowly. His mind raced through the tactical implications, the strategic consequences, the organizational failures this single discovery revealed. He thought of the inter-service rivalry that had defined Japan's military structure. The Army and Navy conducting separate research programs, technical officers dismissed by combat commanders who valued fighting spirit over scientific innovation. The facility's equipment continued its mechanical rhythm, radar pulses sweeping across invisible horizons. Each pulse felt like an accusation. "Catalog everything," Ishikawa ordered, his voice steady despite the turmoil churning inside him. Full technical specifications, manufacturing details, every component, every circuit, every specification. As his team dispersed to their assignments, Ishikawa stood alone among the British machines, processing what this discovery meant. Japan had entered a war assuming their enemies were soft, their technology adequate but not superior, their industrial capacity impressive in scale but lacking in sophistication. This single antenna, this Japanese invention deployed by Japan's enemies, suggested those assumptions were catastrophically wrong. The war was 8 weeks old. Victory had seemed certain, inevitable, a matter of willpower and tactical brilliance overcoming mere material advantage. Now, confronted with evidence that Japan's own scientific achievements had been weaponized against them, Ishikawa felt the first cold touch of doubt. He picked up the British manual one more time, staring at those 3 words, Yagi Array Antenna. A question formed in his mind, one that would define the next 3 years of technological awakening and mounting horror. If this is what the British built, what have the Americans already created? To understand how Japan's military came to ignore Yagi's antenna, one must look back to the 1,930 seconds a decade when Japanese scientific institutions possessed genuine brilliance, but lacked the organizational framework to weaponize it. Before we continue, Click that subscribe button, like this video, and let me know in the comments where you're watching from. It brings me great joy knowing that these war stories and lessons get to people all over the world. Your support helps us bring more thrilling war stories, and trust me, you won't want to miss them. Now, let's get back to the story. The British radar manual lay open on the metal desk, its pages still crisp despite Singapore's oppressive humidity. Lieutenant Commander Haruto Ishikawa had examined dozens of captured documents in the past week: equipment specifications, maintenance logs, operational procedures, all of it standard intelligence material. All of it expected. Page 47 was different. His finger traced the technical diagram, following circuit pathways and component specifications with practiced efficiency. Then he saw it. 3 words in bold English print: Yagi Array Antenna. The room seemed to contract around him. The hum of captured British radar equipment faded into white noise. His mouth went dry. Yagi. He knew that name. Every educated officer in Japan knew that name. Professor Hidetsugu Yagi, Tohoku Imperial University, 1926. The directional antenna that had revolutionized radio wave transmission, an achievement celebrated in Japanese academic circles, published in international journals, recognized worldwide, an achievement Japan's military had apparently never bothered to deploy. Ishikawa's eyes moved from the manual to the equipment surrounding him. British radar sets lined the facility, their antennas mounted on precision-engineered rotating platforms. Each one incorporated Yagi's design. Each one had been detecting Japanese aircraft with devastating accuracy for months. His hands began to tremble. This wasn't captured enemy technology. This was Japanese innovation, perfected by foreign powers, weaponized against its creators. While Japan's Army and Navy had been conducting separate duplicated research programs, jealously guarding discoveries from each other, Britain had been reading Japanese academic journals and building the future of warfare. Lieutenant Arai approached quietly, his face ashen. "Commander, the patent citations reference Tohoku University publications from 1926 through 1928. It's all our research. They've been using it for years." Ishikawa closed the manual with deliberate care. When he spoke, his voice carried the weight of a realization that would reshape everything. If the British have built this, what have the Americans already created? The question hung in the air like smoke from a distant fire, one that was already burning closer than anyone in Tokyo understood. Tohoku Imperial University, Sendai, January 1926. Professor Hidetsugu Yagi adjusted the oscilloscope and watched the waveform stabilize. Behind him, his colleague, Professor Shintaro Uda, made final calculations on the chalkboard, verifying the mathematical principles underlying their design. The antenna array before them looked deceptively simple: a series of parallel metal rods arranged with precise spacing and length ratios. But those ratios, derived from months of theoretical work and experimental refinement, accomplished something previously thought impossible: directional radio wave transmission with unprecedented focus and gain. Yagi activated the transmitter. The receiving equipment across the laboratory responded immediately, signal strength dramatically higher than conventional omnidirectional antennas could achieve. The numbers confirmed what their mathematics had predicted. They had revolutionized electromagnetic transmission. Within months, Yagi published his findings in the Proceedings of the Imperial Academy. The paper circulated through international scientific communities, translated into English, German, and French. European and American researchers praised the elegance of the design. Academic journals featured detailed analyses of the Yagi-Uda antenna's principles. Japan's electromagnetic research stood at the forefront of global innovation. Tokyo Imperial University's physics department rivaled Cambridge and MIT. Osaka University produced groundbreaking work in theoretical mathematics. Professor Yasushi Watanabe was advancing cavity magnetron research, achieving 500 watts at 10 centimeters by 1939, matching Britain's early progress. The scientific brilliance was undeniable. The international recognition was genuine, but recognition in academic journals didn't translate to recognition within Japan's military establishment. While Western powers immediately saw the tactical applications of directional antenna technology, Japan's Army and Navy remained focused on traditional weapons development. Radio research existed, but scattered across duplicate programs, with neither service willing to share discoveries with the other. Professor Yagi's breakthrough entered the global scientific record. Foreign engineers studied it, refined it, adapted it for military purposes. Japan's military filed it away and forgot about it. 16 years later, Lieutenant Commander Ishikawa would discover exactly how catastrophic that organizational indifference had become. Tokyo 1937 Army-Navy Technical Liaison Meeting. The Army research representative sat across from his Navy counterpart, a stack of vacuum tube specifications between them. The Navy officer had requested technical data on improved designs that could advance both services' radio programs. The Army representative's response was immediate. Such information is proprietary to Army research initiatives. The Navy officer nodded slowly. Then our antenna research remains unavailable for Army consultation. Both men returned to their respective laboratories and resumed work on identical problems, duplicating research, wasting resources, reinventing solutions the other service had already discovered. This wasn't cooperation. It was organizational paranoia, masquerading as security protocol. The Imperial Japanese Army and Imperial Japanese Navy operated as rival kingdoms, each maintaining separate research programs, each guarding discoveries not from foreign enemies, but from each other. Technical officers found themselves trapped between services that refused collaboration and combat commanders who viewed scientific expertise with barely concealed contempt. The dysfunction extended beyond inter-service rivalry to career officers trained in traditional warfare. Engineers represented theoretical men whose abstract calculations held little value compared to battlefield experience and fighting spirit. Requests for radar development resources triggered lectures about the primacy of morale over machinery. The consequences became measurable in recruitment statistics. Tokyo Imperial University's engineering department graduated its class of 1,936. Navy recruiters arrived seeking talented officers for technical services. 0 students volunteered. The pattern repeated in 1937. 0 volunteers, 1,938. 0 volunteers. For 6 consecutive years, not a single graduate from Japan's premier technical university chose military service. The message was unmistakable. Brilliant young engineers saw military technical work as a dead-end career path in organizations that didn't value their expertise. Professor Yagi himself would later reflect on this dysfunction with bitter clarity. The Army and Navy certainly never cooperated with each other. That single sentence explained Japan's radar failure more comprehensively than any technical analysis ever could. While Japan's services competed against each other, America and Britain were building something Japan's fractured system could never match: integrated research programs linking military, academic, and industrial resources in seamless collaboration. If you enjoy dramatic, jaw-dropping stories, subscribe to WW2 Archives Declassified. Let's grow this channel to 1,000 subscribers. Dover, England, September 1938. The chain home radar towers rose 350 feet above the English coastline. Steel lattices supporting arrays of Yagi antennas aimed across the channel. RAF operators monitored oscilloscope displays in concrete bunkers below, tracking aircraft movements 100 miles distant. This wasn't a research project. It was an operational network. 20 stations stretched along Britain's southern and eastern coasts, each feeding data to Fighter Command headquarters at Bentley Priory. When German aircraft crossed the channel, controllers could vector RAF fighters to intercept them with precision impossible through visual observation alone. The system had a name that reflected its purpose: Air Defense of Great Britain. Britain had transformed radar from laboratory curiosity into strategic infrastructure. The innovation wasn't just technical, it was organizational. Radar stations connected directly to Fighter Command. Scientists worked alongside military planners. Research priorities emerged from operational requirements rather than academic interest. Chain home represented integrated warfare. Information flowed seamlessly from detection to decision to deployment. Cambridge, Massachusetts, October 1940. The Massachusetts Institute of Technology established the Radiation Laboratory with a singular mission: accelerate radar development beyond anything existing programs had achieved. The U.S. government provided unlimited funding. MIT provided facilities. The military provided operational requirements. Within months, the RAD Lab employed 4,000 people: physicists, engineers, mathematicians, and technicians working in coordinated teams. University researchers collaborated with Navy officers and Army Signal Corps personnel. Private defense contractors sent engineers to integrate manufacturing considerations into prototype designs. Information sharing was mandatory, not optional. When Bell Laboratories developed an improved magnetron design, the specifications circulated immediately to MIT, Naval Research Laboratory, and partner universities. When field commanders identified operational limitations, engineers received feedback within days. rather than months. The RAD Lab didn't just develop radar, it industrialized innovation. Prototype designs moved from laboratory testing to factory production with systematic efficiency. American industry received technical packages complete with manufacturing specifications, quality control standards, and testing protocols. This was warfare as industrial process. Science, military doctrine, and production capacity functioning as integrated system rather than isolated components. The Naval Research Laboratory coordinated directly with university programs. Army and Navy research teams shared facilities, personnel, and data. Academic researchers maintained security clearances, allowing them direct access to field commanders and operational intelligence. Competition existed, but within cooperative framework. Multiple teams might pursue parallel solutions to the same problem, but discoveries were shared systematically rather than hoarded jealously. British researchers traveling to America found colleagues eager to discuss technical challenges openly. American scientists visiting British facilities received complete access to chain-home operations and technical specifications. Allied cooperation extended beyond national boundaries. The contrast with Japan's organizational structure was absolute. Where Japanese services guarded information from each other, Allied forces shared it across oceans. Where Japanese combat commanders dismissed engineers, Allied commanders gave technical officers authority to reshape tactical doctrine. Where Japanese research remained fragmented across duplicate programs, Allied research operated through integrated networks, linking dozens of institutions. By 1941, this organizational advantage had translated into measurable technical superiority. American radar detected aircraft at ranges exceeding 150 miles. British systems provided altitude information, allowing three-dimensional tracking. Integration between radar detection and fighter interception had become doctrine rather than experimental concept. Japan possessed brilliant scientists working in isolation. America and Britain had built brilliant systems through collaboration. The war's outcome had already been determined in laboratories, conference rooms, and organizational structures years before the first shot was fired. Henderson Field, Guadalcanal, August 1942. When U.S. Marines captured the airfield, they also seized an intact Japanese Type 11 Mark I early warning radar installation. Naval Research Laboratory technicians arrived 3 days later to conduct technical evaluation. Lieutenant Commander Robert Hayes led the assessment team. He'd spent 2 years evaluating radar systems at NRL in Washington, British equipment, American prototypes, intelligence reports on German developments. He understood what modern radar technology looked like. What sat before him at Henderson Field wasn't modern. Hayes and his team photographed every circuit, measured every component, traced every connection. They worked methodically for 6 hours, documenting specifications with clinical precision. The circuitry used basic vacuum tube configurations American engineers had abandoned 3 years earlier. Component quality varied wildly. Some parts showed precision manufacturing, while others appeared hand-assembled with inconsistent tolerances. The power supply design was unstable, vulnerable to voltage fluctuations that would degrade performance under field conditions. Hayes measured the antenna configuration and calculated theoretical detection range. His mathematics confirmed what field testing had demonstrated. The Japanese system struggled to detect aircraft beyond 90 miles under optimal conditions. American SCR-270 radar routinely tracked targets at 150 miles or more. The transmit-receive switching mechanism used a design American engineers had prototyped in 1938 and rejected as insufficiently reliable for military deployment. The Japanese had fielded it as their standard solution. Hayes sat back and stared at the equipment for a long moment. Then he wrote a single sentence in his preliminary assessment that would reverberate through intelligence channels to the Pentagon. Evidence suggests Japanese radar development lags 3–5 years behind current Allied capabilities. 3 to 5 years. In peacetime, that gap represented academic interest. In warfare, it was measured in casualties. Ships sunk because they couldn't detect threats beyond visual range. Aircraft shot down because radar-directed gunfire found them first. Battles lost because one side could see the enemy approaching, while the other remained blind until contact. The verdict was delivered. The evidence was irrefutable. Japan was fighting yesterday's war with yesterday's technology. Corregidor, the Philippines. May 1942, Commander Teishi Nakajima opened the equipment cabinet of a captured American SCR-270 radar and found himself staring at manufacturing quality that seemed impossible for field-deployed military hardware. Every component sat in precisely machined mounting brackets. Wiring followed color-coded standards with consistent routing. Vacuum tubes were identical units, each stamped with standardized part numbers, interchangeable across the entire system. Nakajima had studied electrical engineering at Tokyo Imperial University. He'd worked on Japan's early radar prototypes. He understood electromagnetic theory as well as any scientist in the Pacific Theater. He'd expected competent engineering, perhaps slightly more refined than Japanese systems. The SCR-270 shattered that assumption completely. He pulled a vacuum tube from the American radar and examined it under magnification. The internal elements showed uniform spacing, with tolerances measured in hundredths of millimeters. He retrieved a tube from captured Japanese radar for comparison. The difference was humiliating. The Japanese tube showed visible manufacturing variations, hand-adjusted elements, inconsistent assembly quality. "Look at this," Nakajima said quietly to his assistant, Lieutenant Saito. He held both tubes side by side. "The Americans are producing these by the thousands, each one identical, each one meeting specifications that we achieve perhaps one time in 10 attempts." The SCR-268 fire control radar revealed even more troubling capabilities. The system could track aircraft with precision sufficient to direct anti-aircraft guns automatically. Integration between radar tracking and fire control represented sophistication. Japanese engineers had discussed theoretically, but never implemented practically. That evening, Nakajima's team compiled preliminary findings. The conversation, documented in his personal journal, revealed growing horror among technical officers who understood exactly what they were seeing. The vacuum tube standardization alone represents industrial capacity we cannot match, Lieutenant Saito observed. They're not hand-selecting components that meet specifications. They're manufacturing to tolerances that make selection unnecessary. Nakajima stared at the American equipment. His voice carried the weight of recognition. This is not laboratory equipment adapted for military use. This is purpose-built military technology emerging from systematic industrial production. The gap wasn't theoretical. It was industrial. Tokyo, August 1943. For the first time in Japan's modern military history, the Imperial Japanese Army and Imperial Japanese Navy took an unprecedented step. They formed the Army-Navy Radio Technology Committee, a formal structure for radar research, cooperation between services that had spent decades treating each other as rivals rather than allies. The decision came not from strategic wisdom, but from material desperation. Professor Hidetsugu Yagi accepted appointment to lead the committee alongside Professor Yasushi Watanabe and the venerable Professor Hantaro Nagaoka. These men represented Japan's finest scientific minds. Under different circumstances, their collaboration might have produced remarkable breakthroughs, but circumstances were no longer different. They were catastrophic. The first committee meeting revealed the depth of Japan's material crisis. Nickel, essential for vacuum tube manufacturing, had become so scarce that the military purchased coins from civilians and melted them down for component production. Copper supplies had dwindled to the point where engineers scavenged wiring from damaged equipment rather than fabricating new circuits. Vacuum tube production, once handled by specialized manufacturers, had been subcontracted to small workshops lacking precision equipment or quality control processes. Tubes arrived with failure rates exceeding 40%. Those that functioned initially often failed within weeks of field deployment. Professor Watanabe compiled a report on available skilled personnel that read like an obituary for Japan's technical capacity. Experienced radar engineers were being drafted into infantry units, their irreplaceable expertise thrown into the grinding attrition of island combat. Universities that once trained electrical engineers now operated on skeleton staffs, their laboratories stripped of equipment for military use. The committee could organize cooperation, but it couldn't conjure resources that no longer existed. In a converted warehouse outside Tokyo, Lieutenant Hiroshi Tanaka read the committee's organizational directive and wrote in his diary, "We are asked to achieve precision with components manufactured by workshops that measure tolerances with calipers instead of optical instruments. We submit designs requiring materials that no longer exist in Japan." Cooperation had finally arrived. 3 years too late. Pacific Theater, late 1944. While Japanese engineers struggled with vacuum tubes that failed 4 times out of 10, American radar technology continued its relentless evolution. B-29. Superfortress bombers began appearing over Japan, equipped with APQ-13 and APQ-7 Eagle bombing radar. These systems allowed American crews to navigate through cloud cover, identify targets through darkness, and conduct precision attacks that Japanese forces had no capacity to counter. The bombers operated with what seemed like supernatural awareness, finding cities obscured by weather, locating specific industrial facilities through smoke and haze. Fighter interceptions that should have been impossible became routine for American forces. Ground controllers vectored U.S. fighters toward incoming aircraft with uncanny accuracy. Japanese pilots described emerging from cloud banks to find American fighters already positioned for attack, as if the enemy possessed clairvoyant knowledge of their location. They weren't clairvoyant. They were simply reading radar displays. Naval Combat Information Centers revolutionized how American ships processed tactical information. Radar data flowed into centralized plotting rooms, where officers maintained comprehensive pictures of battle space, hundreds of miles in radius. Multiple ships coordinated defenses seamlessly, sharing targeting data in real time, directing fighter coverage with precision. Japanese commanders couldn't approach. Japanese naval forces, still relying on visual observation and radio reports, fought blind against enemies who could see the entire tactical situation simultaneously. In Tokyo, radar engineers read intelligence summaries describing these American capabilities with growing despair. They understood the technical principles involved. They could explain how integrated radar networks achieved such coordination, but understanding a system and possessing the industrial capacity to build it were entirely different challenges. Captain Kenji Yamada wrote to his brother serving in the Philippines, "I have designed a radar system that could detect aircraft at 120 miles range. The specifications are sound, the mathematics are correct, but we cannot build it. The vacuum tubes we need don't exist. The manufacturing precision required exceeds our current capacity." The gap identified at Guadalcanal, 3 to 5 years behind, wasn't static. It was widening. Every month, American technology advanced, while Japanese capacity collapsed further. If you enjoy dramatic, jaw-dropping stories, subscribe to WW2 Archives Declassified. Let's grow this channel to 1,000 subscribers. Battle of the Philippine Sea, the 19th of June, 1944. American carrier radar detected incoming Japanese aircraft at distances that allowed U.S. fighters to intercept them 75 miles from the fleet. Japanese pilots, trained to expect engagement near their targets, suddenly found themselves under attack, with fuel reserves already depleted by the long approach flight. The air battle that followed earned a nickname among American pilots that would haunt Japanese naval aviation for the remainder of the war: the Great Marianas Turkey Shoot. Japan lost 476 aircraft. American losses 130 aircraft, with all naval vessels preserved intact. This wasn't combat. It was systematic execution enabled by technological supremacy. Commander Nakajima read the battle reports in his Tokyo office. He understood exactly what had happened. American radar had transformed the engagement from a battle into a slaughter. Japanese pilots, brave, well-trained, experienced, had been annihilated because they fought an enemy who could see them coming from beyond the horizon. He opened his journal and wrote a single line: "We sent our pilots to die in a battle already lost by organizational failure years before they took off." The mathematics of radar-directed air defense were brutally simple. Anti-aircraft guns equipped with radar fire control needed approximately 4,100 rounds per aircraft kill. Without radar guidance, that number exceeded 20,000 rounds per kill. For a nation whose industrial capacity was collapsing under relentless bombing, that difference represented the gap between viable defense and systematic slaughter. But statistics became visceral reality at Philippine Sea. American carriers detected Japanese strike packages while they were still assembling over their own fleet. Fighter directors vectored interceptors with three-dimensional precision altitude, bearing, range, all calculated and communicated before visual contact occurred. Japanese formations never reached American carriers. They were intercepted, engaged, and destroyed by fighters, guided to them with mechanical efficiency. Lieutenant Tanaka, working on radar prototypes in Tokyo, wrote in his diary after learning the battle's outcome, "We congratulated ourselves on our spiritual strength. We trusted that determination would overcome material disadvantage. We believed America was soft, individualistic, incapable of the sacrifice required for victory. We were catastrophically wrong. The lesson was complete. Courage cannot defeat systematic industrial supremacy." Hiroshima, the 6th of August, 1945, 8:15 a.m. The B-29 Enola Gay released its payload at 31,000 feet. As the bomb fell toward the city below, a radar altimeter activated its signal transmitted and received through a specialized antenna array designed to determine precise detonation altitude. The antenna was a Yagi-Uda array at exactly 1,900 feet above ground level. The radar trigger initiated the firing sequence. The atomic bomb detonated with a force equivalent to 15,000 tons of TNT, obliterating 4 square miles of Hiroshima in an instant. 3 days later, Nagasaki experienced the same devastation, same delivery method, same radar-triggered detonation system, same antenna design. Japan's invention, perfected by foreign powers, had enabled the weapons that ended the war. Lieutenant Commander Ishikawa learned this detail from American technical documents during the occupation. He sat in silence for several minutes, processing the complete arc of organizational failure that began in Singapore 3 years earlier. February 1942. He had discovered Yagi antennas in British radar facilities, realizing Japan's military had ignored their own scientists' breakthrough while enemies weaponized it. August 1945. That same technology had helped deliver weapons that made further resistance impossible. The symmetry was devastating. The irony was perfect. Professor Yagi's 1926 invention had traveled a path Japan's fractured military system could never have facilitated, published in Japanese academic journals, adopted by British and American researchers, refined through integrated research programs, mass-produced by systematic industrial processes, deployed across thousands of radar installations, and finally, incorporated into the fusing mechanisms of weapons that represented the ultimate expression of scientific and industrial supremacy. Japan had produced the seed of innovation, The West had cultivated it into a weapon that decided history. Ishikawa closed the technical documents slowly. In that converted office in occupied Tokyo, surrounded by the ruins of a nation that had valued fighting spirit over systematic excellence, he understood the final lesson with absolute clarity. Modern warfare is not won by individual brilliance. It is won by nations that possess the organizational capacity to transform innovation into industrial reality. Japan had brilliant scientists. America built brilliant systems. The war's outcome had been determined by which philosophy prevailed. Tokyo, October 1945. In a converted office building that had somehow survived the firebombing, surviving Japanese engineers gathered to compile technical assessments for the occupation authorities. Commander Nakajima, Lieutenant Tanaka, Captain Yamada, men who had spent years watching Japan fall further behind while understanding exactly why it was happening. The American technical officers requesting these reports expected defensive rationalizations, perhaps claims that Japan's defeat stemmed from numerical disadvantage or resource scarcity. They received something different: unflinching recognition of organizational failure. Commander Nakajima's final wartime journal entry, written the day after Japan's surrender, contained no bitterness toward American forces, no claims of technological theft, no appeals to fighting spirit or noble sacrifice. Just clinical assessment. When we examined American radar in 1942, we thought we were looking at advanced machinery. We were wrong. We were looking at the physical manifestation of organizational philosophy. We saw systems that emerged from cooperation we never achieved, industrial capacity we never built, and scientific integration we never attempted. Lieutenant Tanaka submitted his radar development records to American evaluators with a cover letter that would later be preserved in U.S. military archives. Japan possessed scientists whose theoretical knowledge matched or exceeded Western capabilities. We understood electromagnetic principles as thoroughly as any researchers at MIT or Cambridge. But modern warfare had evolved beyond individual genius. Radar was not a device. It was a network requiring coordination between research, production, deployment, and tactical doctrine. It required services working together, engineers respected by commanders, and industrial capacity organized for rapid innovation. Japan possessed none of this organizational infrastructure. Captain Yamada, in his final official report, wrote the sentence that would define how Japan's technical community understood their defeat. We did not lose to better minds. We lost to better systems. The lesson was complete. The accounting was honest. The recognition was absolute. Courage could not substitute for cooperation. Spirit could not overcome systematic excellence. Pride could not replace organizational competence. That was the truth Japanese engineers learned, purchased in blood, fire, and the ashes of a nation that chose rivalry over unity. Don't just watch, subscribe. Help W. Archives Declassified Hiruno. 000 subscribers.